Hello and welcome to this video on rules for differentiation, a part of the Mathematical Methods Units 1 and 2 course here in Australia, but trust me, useful throughout the whole world. I can't think of a country that doesn't do differentiation. Now, my name is Darren from Maths Guru. Really good to see you. Thanks very much for following the course. Hopefully it's going to be useful for you. If you can do me a massive favor and subscribe to me on YouTube, that'd be massive. Turn off your notifications. Trust me, I don't spam you. But if you don't want to hear from me again, that's awesome. But just by subscribing, other than sounding incredibly needy, it just means that I know that people out there are actually watching and for me to continue creating these videos, right? Otherwise, I'm sitting in here talking to myself, which normally would put me in some sort of an asylum. I'm on TikTok as well, if you can follow me on there, and head over to mathsguru.com. All of the things you see behind me, the notes that I write all over, are downloadable from Maths Guru. You can put them in your summary book, slice out sections. Great to know. And thank you very much to Cambridge for allowing me to use your worked examples. You guys literally rock. Thank you so very, very much. Now, as we can see, what am I going to go through here? Well, this is going to build on the previous lesson where we really talked about, where the differentiation by first principles come from, and it's leading me into this lesson here. So we're going to need to learn about how to use the CAS, what the different rules are, how to find the gradient of a tangent at a point, because that's what differentiation really is finding the value of the gradient of the tangent that just touches a curve at a particular point. And when I was teaching this in previous schools, I'd probably actually get my year 11s and 12s to sort of chant that, because believe it or not, many of them just didn't realize what it was we were doing. But you're better than that, aren't you? Of course you are. Now, recapping what we did before, we came up with this formula here, which was effectively differentiation from first principles. And it was the idea that if we have a curve, we can actually sort of make our secant shorter and shorter and shorter, getting closer and closer to a particular point. And we found that by using limit notation, we could end up with an approximation for the gradient at a particular point, or more importantly, the gradient of a tangent at a point. We're going to build on this to try and make life a little bit easier, because differentiation shouldn't be that hard. I know a lot of people turn around and go, that differentiation from first principles sucks. I get it, which is why normally, funnily, I teach it at the very, very end of differentiation. All right, because I'm trying to follow the Cambridge sequence here. Obviously, that's the first thing they do, but maybe I should suggest that people watch it as the last video. But what we noticed was, in previous videos, when I had y was equal to x squared minus 2x, then the differential f dashed of x became equal to 2x minus 2. Now, obviously, there's got to be some sort of pattern to how this is happening. Likewise, when we had y was equal to x cubed plus x, my f dashed of x became equal to 3x squared plus 1. Now, how is this happening? Is there a shortcut to be able to do this? Well, absolutely there is. And as I say here, the shortcut to differentiation is for each term in an expression or an equation, we basically multiply by its power and then subtract 1 from the power. So if we look at x squared, my power is 2. I'm going to multiply what was in front of there, which is actually 1, by 2. The x stays the same, and I'm going to take 1 off the power. But we don't write x to the power of 1 because that doesn't make any sense. If I look at minus 2x, that's currently got a power of 1. So I'm going to multiply my power by what's in front of my term, or what's my coefficient. So minus 2 times 1 is minus 2. X, and I take 1 off the power, which becomes power to the 0. And we know that anything to the power of 0 is in fact 1. And so there we go. So that explains how we got the 2x and minus 2. Just checking this next one. X cubed plus x, well, does the 3 multiply by the power? Yes, by the coefficient. Yes, that becomes the 3, and I took 1 off the power. Right, again, x, just do that one here. I've got x to the power of 1. Take the 1 down and multiply by what the coefficient was, which was 1, times x to the power of 0, and anything to the power of 0 becomes 1. And so in that situation, anything with an x in it appears to just become a number. Oh, we're liking this. And that's very much what the derivation of x is, or the derivative of x to the power of n is. Now, what I'm saying there is n is a floating number, n is a power. And so if I had y was equal x to the power of n, then what I've got, f dashed of x is equal to, or bring the power down, or multiply by the power, that becomes n times x to the power of n minus 1. That's just formalizing what it is. And I think a lot of the thing that confuses people with methods is the notation. Now, at the moment, we're just going to assume that it applies to positive numbers only. Okay, so just the positive n values, right? Now, in which case we've got n's of 1, 2, and 3. Now, there are lots of things and lots of rules that sort of apply to differentiation, and the more you do it, the more that these just become second nature. But if we were to have a constant, right, it will differentiate to 0. And I'm going to show you why. If I had the number 3, if I had, for example, y is equal to 3, well, that doesn't have an x in it at the moment, does it? So when we do f dashed of x, all right, so differentiate with respect to x, you're going to turn around and say, well, where's the x? Well, actually it is. It's x to the power of 0. See what I've done there? Because anything to the power of 0 is 1. So now let's follow the rules. You multiply the coefficient by the power. Well, 3 times 0 gives me 0. And I take 1 off the power. So that would become x to the power of minus 1. But to be fair, it doesn't actually matter what that x to the power is because I've already got 0 times. And anything times by 0 becomes 0. So, and again, it doesn't matter which number I choose. If I chose 10, if I had y was equal to 10, then f dashed of x. If we have that there, that would be x to the power of 0. 0 times 10 would be 0 times x to the power of minus 1. And again, that becomes 0. So a constant differentiates to 0. And that becomes really important in a later video. A linear function. If we think about a linear function, what do we know about the gradient all the way along a straight line? Absolutely, it's constant. It stays the same value. So for example, if that there was y is equal to 3x plus 2, for example, we know the gradient because we've been taught it previously before, y equals mx plus c. My gradient all the way along there would equal 3. And again, when you're differentiating, you're finding the value of the gradient of the tangent to a point along that line. Well, all points will have the same tangent. So if I've got y is equal to 3x plus 2 there, then f dashed of x becomes equal to, well, that's 1. So 3 times 1 gives me 3. That becomes x, take 1 off the power, x to the power of 0, plus, well, that's 2x to the 0. But hold on a moment, I've just told you that any constant differentiates to 0. So that's going to become plus 0. X to the power of 0 is 1. 3 times 1 gives me 3. And there we go. So the differential of 3x plus 2 is 3. Well, of course, because we know that we're finding the gradient of the tangent to a point, and all of the points there have a gradient of 3. So that's nice to know for a linear function. What about if we have a multiple of a function? What about if I have something that y was equal to 3x squared? Well, by the following of the rules, f dashed of x, that gives me, well, what I'm going to do is I'm going to do 3 times, and I'm just going to differentiate x squared. What do? I bring the power down, 2, x to the power of 1, yep, take 1 off the power. And so what we're really saying is here that that's 3 times 2x. Well, okay, so a multiple of a function has the same multiple of the derivative, yeah? So in which case, that just becomes 6x. Personally, I've never thought of it that way. I'm putting it in there because it's in the new study design or in the new textbook. But as far as I'm concerned, I would always have done 3 times 2, which gives me 6. Take 1 off the power. The sum and difference of functions, right, when you do the derivative, and I sort of did an example before, when I have y, it was equal to 2x squared plus x, for example, well, that's a sum of a function, right? So the derivative of the sum of a function is the sum of the derivatives. What it means is you just differentiate each part. So in which case there, f dashed of x, right? So differentiating that with respect to x gives me, well, 2 times 2 gives me 4, x, power of 2, take 1 off to the power of 1, don't need to write it, plus x, well, that's x to the power of 1. 1 times 1, which is 1. X to the power of 0 is 1. So there we go. I just get 4x plus 1. Likewise, if that was, subtract, it doesn't make any difference. If it was 3x cubed minus 2x squared, you just differentiate each individual term, just sort of keeping the minus sign in there. So f dashed of x there would be 9x squared, yeah, because the 3 times the 3 is 9, take 1 off the power, minus, well, 2 times 2 would give me 4, x to the power of 1. Why is it 1? Because it was a 2, take off the 1. And the more that you do this, the more it becomes second nature. But the problem is it becomes formulaic, and you get to a point where you forget what it is you're actually doing. You're like, well, why am I doing this? A method is about understanding the why. When you have a curve, work out what it looks like. That's going to make life so much easier. So find the derivative of that, i.e. differentiate it. So if I've got x to the power of 5 minus 2x to the power of 3 plus 2, then let's just say that that's y equals, so f dashed of x becomes equal to, right, 5x to the power of 4. So I've multiplied by the power, 5 times the coefficient of 1. Take 1 off the power, minus 2 times 3 is 6. X, take 1 off the power squared. And a constant differentiates to absolutely nothing. Congratulations. And there we go. 5x to the power of 4 minus 6x squared. Find the derivative of f of x equals that, and thus find f dashed of 1. So we've got f of x is equal to 3x cubed minus 6x squared plus 1. Right, differentiate it. All right, so f dashed of x is equal to 3 times 3 is 9x squared minus, so 6 times 2 is 12x squared, take 1 off power, and the constant goes. Again, it gets faster. Now, in a previous school, I got told off by VCAR. Why? Because pretty much 1 year, not one of my students had picked up the notation of f dashed of 1. And so failed pretty much every single question. I don't know why, because I talked about it literally all of the time. But I'm now making it a little bit more explicit. What do we notice? Well, when we compare this with this, what do I notice? Well, the x has become a 1. So that f dashed of x and f dashed of 1 is basically saying everywhere you see an x in the differential, replace it with 1. So there we go, I get 9 times 1 squared minus 12 times 1 gives me 9 minus 12, which hopefully is negative 3. Now, what does that actually mean? And again, the context is important. That is telling me now that the gradient when x equals 1, so my gradient when x equals 1 is equal to negative 3. So at that point, the gradient of the tangent to the curve at the point where x equals 1 is negative 3. So what I know is it's something along those lines, at one point there, right? Again, really, really important. Now we can use the CAS to do this. Now I'm going to use the TI Inspire. For those of you who've got a class pad, trust me, it's pretty much the same. You guys hopefully have the ability to sort of translate. Where they're massively different, I promise you, I will let you know. So I'm going to do a calculator screen here. So what I'm going to do is hit this button here, and you'll notice I've got lots of sort of pre-filled in sort of functions. Hit that one there, he says, hoping that his eyesight is good. Right, so because we're differentiating with respect to x, I'm going to put an x down here. And then what am I going to do? I'm going to actually type in my function here of 3x cubed minus 6x squared plus 1. Oh, now, what do you notice there is that you've got to be very careful with this calculator to make sure that you put the cursor in the right place, otherwise it will go a little bit haywire. So 3x cubed. Now I'm going to hit enter. Lo and behold, out comes 9x squared minus 12x, which is pretty much what I got before. Ka-ching, very, very happy. Now again, find when that is equal to 1. Now what I can actually do again is copy that down. Now when I put a pipe symbol, right, and that's that little vertical line there, he says trying to find it on the calculator. Where are you? You're there, control above the equals, and that pipe symbol. You can actually substitute values in. So I'm going to say when x is equal to 1, when I hit enter, out comes negative 3. So what your calculator is doing there is differentiating it, and then once it's done that, it's substituting the value of x equals 1 into it. Using a CAS, this is a CAS course, it's going to make your life so much easier. Finding the gradient of the tangent of a line. All right, so I've already talked a moment ago that when we had f dashed of 1, we were finding the gradient of the tangent of the line at that particular value when x was equal to 1. Right? So for the curve determined by the rule of, we've just had that one, find the gradient of the tangent to the curve at the point 1, negative 2. Well, when I look at a coordinate, they're always giving me a value. So when I got 1 minus 2, that's an x value and a y value. But what I want to make clear is that when you differentiate, and I bring my calculator back up, when you differentiate, because it's exactly the same function, what we noticed was the differential is only in terms of x. So I don't care what the y value is, I just want the x value. So we know that f dashed of x there is equal to 9x squared minus 12x. So what I'm now saying is, well, I know my x value is 1. I want to find the value of the gradient at 1. So we get f dashed of 1, and you're going to turn around and say, hold on a moment, aren't you just reusing the same example over and again? Possibly, but what I'm trying to tell you is how important this is, right? To get this fundamental thing. If you get this, the rest of this exercise and textbook, I swear, is pretty much the same. We just teach you different techniques. So again, where I see an x, I'm going to replace it with 1. 9 minus 1 squared minus 12 times 1 is equal to -3. So our gradient there is going to be -3 at that one point and one point only. If I go to a different point, it's going to give me a different gradient. Now, because Barry is a pain in the butt, and if you don't know who Barry is, he's that muppet who sits in a room in Australia, no lights, no friends, no ability to communicate with humanity, just a copy of a Sudoku book sitting beside him, trying to find the most complicated ways of teaching maths. In the United Kingdom, we got rid of him twice. He came back. No. But anyway, over here he seems to be paid to try and make things really, really complicated. So we can write the differential in a different way. And again, if you go back to, if I bring back my calculator, you notice here that this here was a way of doing it. Now, actually, in a minute, I'm going to talk to you about that. That's actually called operator notation. But there are lots of ways of writing the same thing, and that's where we confuse you in methods. So firstly, Leibnitz notation is given by dy by dx. So if I had, I don't know, y is equal to 6x squared plus 4x, then we can say the differential is dy by dx. All right, so what that means is we are differentiating y with respect to x. And that means we're just differentiating the x sections. Later on, if you do specialist maths, you can differentiate y's and x's and all sorts of stuff with implicit differentiation, but won't worry about that for a moment. So in that situation, we would write 12x plus 4. Now, if you're not sure where I got that from, pause the video, have a look, try and work out by multiplying by powers and taking one off the power. So that's one way of doing it. We can also do y dashed to mean exactly the same thing. That's another notation, is y dashed, or as you've seen, I could write that as f dashed of x is equal to 12x plus 4, because we can replace y and f of x are the same thing. They're exactly the same thing. So much notation, so little time. If we look at this one here, we can also change the letters. There's another way to try and trick the life out of you, is by changing the letters. So if we have y equals t squared, well, I can't write dy by dx. Why? No. X? No. I've been humorous. We can't write dy by dx because we don't have x in this. I can't differentiate y with respect to x because I've got t squared. So there, I have to do dy by dt. But the rules are exactly the same thing. I don't care what the letter is. The process is multiply the power by the coefficient and take one off the power. So that would just become 2t. What about the next one? X is equal to t cubed plus t. Well, now I can't do dy by because it doesn't start with a y. But again, I can do dx by dt, which gives me a 3t squared plus 1. And what about the next one? Z. Oh, let's just throw another letter in. Z is equal to 13x cubed plus x squared. Now, can you guess what this is going to be? Okay, I gave it to you in the question. But it starts with the z equals, so I'm going to do dz, but divided by what pronumeral has been left on the right-hand side, x. So in that situation, dz by dx, which would be, oh my goodness, 39x squared plus 2x. Don't get tricked, right? I'd say over and over again, maths is a huge trick, and that's all it is. Once you know the basics and you can see the tricks, life is easy. Right, for y is equal to x plus 3 all squared, find dy by dx. There's a number of questions here, 4 questions. Let's go through them and notice the different way that it's asking. Every single thing asked in a slightly different way, but all the same. So first one, we've got y is equal to x plus 3 all squared, and we've got to find dy by dx. So dy by dx. Well, I've got a bit of a problem first because I don't know how to do that. I've not got any rules yet that show me how to multiply something with a squared outside. Later on, we will do. Now, we're not. So what you'd actually do is you'd multiply that out to become x squared plus 6x plus 9. Now, if you didn't get that and you think that's just x squared plus 9, you have to stop now. Right, you've got to go back and rework out that, how to do it. Remember that x plus 3 all squared is the same as x plus 3 times x plus 3, which means you will actually have to do FOIL or whatever other way you think about it. A lot of people make a mistake here and then get that as just x squared plus 9. It isn't. Now, having got that, I can work out what dy by dx is. Have I got my pronumerals right? Yep, starting with a y, I've got x's in it, by doing 2x plus 6. Again, the 9 is a constant, so it just goes. 6x becomes just 6, and the x squared becomes 2x. So there we go. So that's my first thing. What about the next one? For z is equal to 2t minus 1 squared, t plus 2. Right, again, I've got to multiply all this out. So actually, before I go any further, I can't differentiate this until it's actually all multiplied out. So what I'm going to get here, I'm going to get 4t squared minus 4t plus 1. So that's the squaring of the first one. Multiplied by t plus 2. So that's going to give me 4t cubed plus 8t squared minus 4t squared minus 8t plus t plus 2. Now the reason I've slowed down there is I've actually multiplied that out in the strangest way I've ever done in my entire life, but hopefully it'll make life a bit easier. So I've got 4t cubed, 8t squared minus 4t squared is plus 4t squared, minus 8t plus t gives me minus 7t plus 2. Hopefully these are all correct. Now I can do dz by dt, making sure I've got my pronumerals correct there, as 4 times 3 is 12, t take 1 off the power, 4 times 2 is 8, t take 1 off the power, minus 7, because anything with just the letter in it becomes just a pronumeral, and 2 has gone. So there we've got dz by dt. Okay, so as I've run out of space on that one, let's go on to the next one. So what have we got here? We've got y is equal to x squared plus 3x, all on x, find dy by dx. Now again, the shame of methods is we try and trick you with all sorts of stuff. So here, you can't actually differentiate that. Later on you will be able to, because we used the quotient rule, but it actually makes life easier if we realize that we can actually split that up into x squared on x plus 3x on x. Now I say that any time anything on the top has got pluses, you can split those up into individual terms. Well, hold on a moment, that makes life a little bit easier, because x squared divided by x is just x, and 3x divided by x is actually just 3. So actually that's just become trivial now, because y becomes equal to x plus 3. So dy by dx becomes equal to 1. Now again, y, because the constant goes, and that x has got to the floaty 1, and the 1 times the 1 goes 1, and there we go. Differentiate y equals 2x cubed minus 1 with respect to x. Again, it's just the same stuff over and over again. So we've got y is equal to 2x cubed minus 1. So when you differentiate with respect to x, it's just saying differentiate the x bits. 2 times 3 is 6x squared, and the number is there. So there we go. There's a number of different examples utilizing a number of tricks. And then again, as I said a moment ago, there's another way of doing this. There's what we call operator notation, and that's the one that your calculator uses. Yeah, so when I put this in, that's your calculator, where it puts the d by dx and in brackets the thing you're actually differentiating. But it's exactly the same. So in that situation, I'm just differentiating what's inside the brackets. 5x is just going to become 5 minus, well, 4 times 3 gives me 12. X, take 1 off the power, gives me 2. There we go. Differentiate what's inside here with respect to z. Job done. We can do that. So it's going to become 10z minus 4. Again, the more you do this, the quicker you get. 6z cubed, which gives me 6 times 12, 18. Z squared, 4 times 2 gives me 8z. Ka-ching. Faster and faster and faster. Yeah? Now, finding the point given a gradient. For each of the following curves, find the coordinates of the point on the curve at which the gradient of the tangent line at that point has the given value. So we've got, let's do the first one. We've got y equals x cubed. So we've got y is equal to x cubed. I'm going to do dy by dx is equal to 3x squared. Okay, so we've differentiated it, but that's telling me the gradient of the tangent of the point. This here is basically an equation that says you can find the gradient of the tangent at that point, at any point, so long as you know the x value. But hold on a moment, they're giving me the gradient. That's all right. What you do forwards, you can do backwards. Or what you can do forwards, you can do backwards for the camera. Right, what have we got here then? So they've given me the gradient. They've told me dy by dx. So I now know that 8 is equal to 3x squared. I can solve this by using my calculator. So I can type in here, solve, open brackets, 8 equals 3x squared, for x if you will, and there we go. We get our x values as minus 2 root 6 on 3, and x is equal to 2 root 6 on 3. Now in a moment I'm going to show you another way of doing this, which actually blew me out of the water when I learned it, funny enough, 2 nights ago. What's confusing or what's annoying here is your calculator goes x equals or x equals. It's not easy to substitute those values in anything else a little bit later on, but the CAS should make your life easier, shouldn't it? So must be a way of doing it, and I'll show you in a moment. Let's go back to the next example. So what have we got here? We've got y is equal to x squared minus 4x plus 2, and the gradient is equal to 0. Now again, later on that becomes hugely important. Finding where there's a 0 gradient, which is a horizontal line, massively important. So let's do dy, he says, not being able to write anymore, by dx is equal to, that is going to become 2x minus 4. Well, they've told me the gradient is 0, so dy by dx is 0. So I have 0 is equal to 2x minus 4. 2x is equal to 4, x is equal to 2. So in that situation, there was only one x value. There's only one place when x equals 2 to find the gradient of 0. Now obviously in many cases, just knowing an x value is fairly pointless. We'd probably want to find a coordinate. Spoiler alert, it's coming up. What's the next one? We got y is equal to 4 minus x cubed. The gradient is negative 6. Right, well, whenever I talk about gradients in these questions, I now automatically differentiate. The 4 goes, it's a constant, it disappears. Minus 1 times 3, which is minus 3 x squared. And again, a lot of people get tricked there. They ignore the minus sign as well. My gradient there is negative 6. So what do I get here? I get minus 6 divided by minus 3, which is 2. So I get x squared is equal to 2. He says, turning the CAS off. Sorry about that, guys. All right, so hopefully you catch up with the working out there. I get so excited with this, I forget to turn the CAS off, but we're getting better. So x squared is equal to 2, so in which case x becomes equal to plus or minus the square root of 2. And again, don't forget that plus or minus. It's really, really important. And again, as the course goes forward, you will be told over and over again what the value of gradients are. They'll say the gradient is. That is a big flashing light to turn around and say, well, actually just do what you need to do to differentiate the function and then put it equal to whatever they're telling you. All right, here we go. The CAS, there is a way to make life easier for you. And we got this question here again. So obviously what I'm about to show you, it seems quite long-winded to be able to do this. I'm going to menu actions and I'm going to go clear history. Now, first thing you want to do with methods, in many cases, you want to actually define a function. You want to be able to get your calculator to remember a particular function. And where I see y, I put f of x. So I can say define f of x equals x cubed. All right, so there's my definition of f of x. But there is another way of doing it if you don't want to keep doing that. And that is actually above the little book symbol here. And I'll show you in a moment. I can actually go fx and I say control, that little book symbol there, colon equals. That is computer programming language for effectively defining. So I can actually do x cubed, same. What do I want to do now? I want to differentiate that function. So I'm going to do this, hold up that with my operator notation d by dx of f of x. Hit enter, and lo and behold, out comes my 3 of x squared. Now you're going to turn around and say, okay, what's that got to do with anything? We now know that dy by dx from the calculator gives me 3x squared. Yeah, and you're going to say I could have done that in my head. I know, but later examples get harder. We know the gradient. We've got 8 is equal to 3x squared. I'm going to write that in a slightly different way. I'm going to now say, let's think of that as 3x squared minus 8 equals 0. And believe it or not, your calculator has a function, I mean the TI Inspire does, I'm not really sure about the ClassPad, that can actually solve to find zeros. And what that means is when anything is equal to 0, you can actually get it to solve. So I'm going to go menu, algebra, zeros. Now it's just going to type zeros there, and what you do is you put your equation, comma, what you're trying to solve. So in this situation, 3x squared minus 8, comma, x. I don't need to put the equal 0 in because that's what the 0 is doing. We're saying, well, this particular part of the function is equal to a. And you're going to turn around and say, oh, that's funky. Yes, really funky, but also really, really helpful. Why? Because what you notice is previously, when we did the previous example, what did we find? Well, we had x equals or x equals. So if we looked at this, the calculator gave me this for the x equals. When I go back to looking at this now, we notice it's in curly braces. And the great thing about that is your calculator can do something with that. It's like a set of values. What if I wanted to now find the coordinates where my gradient was equal to 8? Well, I don't just want the x values, I'd want the y values as well. Well, because I've defined my function, I can actually say f, open brackets, highlight that, put it in. Now, because of those curly braces, what's going to happen is it's going to substitute both of those values into my function of x, which I've defined, and give me my y value. So now, beautifully, that first value there is the x value, and that's its corresponding y value. That there is its second x value, and its corresponding y value. Whoa, now a calculator should be able to make life much, much easier, shouldn't it? Could I have done this much easier? Yes, I could have done zeros. I'm typing this, whereas you could use the function. Copy down my differential of, I'm going to do minus 8, comma, x, hit enter, and lo and behold, out comes that. Yeah, so really what I was saying here was that once I had the differential of that, once I did the dy by dx, minus 8, I knew that that was going to be equal to 0, just by effectively rearranging this equation here. Now, if that was too much for you, don't worry about it. Trust me, the more you do, the better you'll get at these calculations, and knowing how to use a calculator is amazing. But after half an hour, that was a flipping long lesson. Why? Simply because it is so important. Get differentiation sorted and you will smash the rest of this course. But for now, if you can, subscribe on YouTube, follow me on TikTok, go to mathsguru.com and sign up. It's absolutely free. You can download the notes behind me. If not, hopefully I'll see you in another video. Oh, tell your mates and your teachers. God, I'm very needy and very demanding. No, I'm not. I'll see you again. Take care. Bye-bye.